Hello everyone, and thank you so much for registering to this second session of a series of webinars on learning data science. Today we'll be talking about data exploration and clustering. So today is the second session of the series. Last time, so it was Tuesday, we talked about descriptive statistics. So those of you who missed the session last time, don't worry, I'll do a small reminder so that you can be up to date and you're able to follow this time. So my name is Jean-Paul Maalouf. I'm a statistics consultant, works with XLSTAT. So XLSTAT, which is developed by the Addinsoft company. So this is a software for statistical analysis, which I will use to illustrate my webinar. Many of you already know the software, and otherwise this is a good opportunity to discover it. So I'll be just like last time, I'll try to be as intuitive as I can. But please note that an hour is too short to present these methods, which may seem very complex. So you'll just have a sense of the way they work and how to implement them in XLSTAT. However, if you'd like to apply them, I strongly advise you to dig deeper into them, so to do some research around the tool we're going to see today. Otherwise, you could get wrong in the implementation of the tools in XLSTAT, and you can be driven to a misinterpretation of results. So please be careful in using these tools. You can also request a tailored training from XLSTAT if you're ever interested in going deeper into these methods. Now, there will be a Q&A session at the end of the webinar. You can submit your questions all along the webinar using the chatting window. I will try to answer as many questions as I can at the end. There will be a recording available of this webinar, and you will get a link to the recording within a few days. So most probably the latest will be early next week. And also you should know that there are handouts and data that you can download using the webinar platform. So there must be a button somewhere which allows you to download the handouts, the presentation, as well as the data. I'll start with a presentation of XLSTAT, who are we? Then I will present the 4 categories of statistical tools, which are already presented last time, before switching to a reminder of the definition of variables, individuals, and a couple of descriptive statistics we've illustrated last time. Then I will talk about exploring and clustering data, which are the topic of this webinar. And I will take one example of each. So I will illustrate data exploration using principal component analysis, or PCA, and I will illustrate clustering data using AHC. So who are we? XLSTAT is a statistical software that works as an add-on to Excel on PC and on Mac. And it's also available for Excel 365 and Google Sheets if you ever want to work on the cloud. So one of the main strengths of this software is that it works in Excel, so you don't need to import your data to another interface or to export your data and to play around with data exportation and importation. Everything happens within the user-friendly interface of Excel, from data capturing to the interpretation of results and the implementation of the analysis. In a few numbers, XLSTAT has more than 220 statistical features. It has more than 150K users worldwide. There are 25 employees working for the software at your service, and 300K monthly visits on the website. The software is available in 7 languages, and we have offices in 3 time zones around the globe, so America, Europe, and Japan. There are 10K monthly downloads of the software. XLSTAT is developed by the Addinsoft company, which is established inside the Data Factory, which is a private lab in Bordeaux, France, dedicated to data science. So there are 5 expert companies around data in this lab. So this lab is quite active in terms of data science. It organizes more than 25 workshops, events, and trainings every year. XLSTAT offers 8 different solutions to meet your specific needs. So there are 3 generalist solutions: Basic, Basic Plus, and Premium. Basic includes over 100 data analysis tools, which allows you to explore, to visualize, to model, and to test your data just in one single interface. Then Basic Plus includes everything Basic has, plus machine learning features. Premium includes the 220 XLSTAT features, so you have everything you need inside Premium. And between Basic Plus and Premium, there are intermediate solutions which are field-oriented. So Sensory for sensometricians. For instance, you will find preference mapping or panel analysis or like penalty analysis to optimize your products within this module or this solution. For life sciences, in the life sciences solution, you will find tools for the analysis of medical and biological data, such as survival analysis, Kaplan-Meier analysis, and omics data analysis. Then marketing includes sophisticated survey tools, such as conjoint analysis or MaxDiff. Forecasting allows for the analysis of time series and risk. And at last, quality, the quality solution, is used for quality control and statistical process control. XLSTAT holds on its website more than 200 tutorials associated to downloadable datasets, and which allow you to introduce you to each of the XLSTAT features. And each tutorial guides you step by step on how to capture data within the feature dialog box, how to configure the dialog box, and at last, how to interpret the results. So each feature is linked to one specific tutorial online. All of these tutorials are available for free online. You can check them even if you don't have an XLSTAT license. Also, StatCafe is a YouTube channel developed by XLSTAT, and it presents different statistical features in short video formats with applications using real-life data. And so it's everything is easily explained and it's very nice to follow. So here are a few families of tools in statistics. Or here's my way of dividing statistical tools into different families or categories. So first of all, descriptive statistics include tools which allow you to describe one single variable or the link between two variables. So for instance, the mean, standard deviation, histograms and box plots, or scatter plots. This is what we saw the day before yesterday. Then exploratory and clustering statistics allow you to easily extract information from large dataset or multivariate dataset without necessarily having a precise question to answer. So if you have a wide dataset and you want to find out patterns inside your data without necessarily expecting anything, you can use exploratory tools such as PCA, which is one of the most commonly used methods in this family. And this will be the focus of today's webinar. Then statistical testing allows you to answer very specific questions whose answer is yes or no, while assuming error risks. So among the most commonly used tools in statistical testing, you will find student's t-test, ANOVA, chi-square, correlation test. And at last, statistical modeling allows you to understand how a variable behaves according to a set of other variables, and also allows you, optionally, to make predictions. So here we will find regression, ANCOVA, and ANOVA. So there are no clear boundaries between these families. So you can find ANOVA here and here, but it's my way of dividing things in order to have a good storytelling from webinar 1 to the last webinar we're going to see together. You will find a link to the recording of the first webinar by clicking on this button here. You can also subscribe to upcoming webinars by clicking on these buttons. Statistical modeling is split into 2 webinars. So one which is more generalist, in which I will be talking about regression, and another one in which I will be talking about ANOVA, because many of you use ANOVA. Here's a small reminder of what we saw the day before yesterday. So what are variables, individuals, and what did we see in descriptive statistics? A variable is a measurable element which can take different values, and there are two main types of variables. Quantitative variables, which can be expressed in terms of numbers. A quantitative variable is a variable that can be quantified. So examples, the number of items in the cart, the size, the weight, the price, the scores from a question which can be scored from 1 to 10 in a questionnaire. And on the other hand, we have qualitative variables which take categorical values and cannot be quantified or ordered. For instance, socio-professional category, gender, geographical origin, experimental treatment. And of course, things are a little bit more complicated than this. So there are many subtypes of variables, but I won't be spending time on these. Let's just stick to this classification of variables. Then individuals or observations are elementary statistical units. So for instance, clients or respondents of a survey or patients following a clinical trial, a plot in a field in agronomical research, a measurement on a machine for statistical process control. And individuals or observations are characterized by variables. Now here's the data set we had used last time. So these are the clients in rows from an online shoe selling platform. So in rows, we have the observations or the individuals who are characterized by variables which are stored in columns. And in most cases, data sets should be organized like this for the analysis, whether it was for XLSTAT or many other software. The data are made up. So as you can see, we have qualitative variables characterizing the clients, origin, gender, preferred brand. We also have quantitative variables expressed in terms of numbers, so height, shoe size, weight, time spent on site, and invoice amount. Here's the summary of the descriptive statistical tools we've seen in the last webinar. And here's once again the link to the recording of the webinar that you can access here. So you will have a link, access to the recording and also to the presentation PDF and to the data. So in order to describe one single qualitative variables, we use frequencies, mode, and bar chart. So if you remember, we had described this column here, preferred brand, by counting the number of occurrences of each brand inside, and we expressed them in terms of frequencies and also in terms of proportions. Then we identified the mode, which is the most frequent category, and the frequencies, we represented them in bar charts and pie charts. Then we described one quantitative variables. We took shoe size, if you remember. So where is it? Here, we took shoe size that we characterized using central tendency, which is the measurement of the middle of the data, and we measured central tendency with mean and the median. We also used indices that reflect the dispersion of the data, so to what extent are the data points spread around the central tendency. So we used standard deviation. We also talked about quartiles, and we used histograms and box plots in terms of visualization tools. Then to describe the link between two qualitative variables, we drew crosstabs or contingency tables. For the link between two quantitative variables, we drew scatter plots, so with one variable on X and another one on Y. Then for quantitative versus qualitative, we drew one box plot per category of the qualitative variable in the same chart. And at last, I want to focus on this one. In terms of transition to the current webinar today, I had shown you one way of displaying the link between three variables, two quantitatives and one qualitative. So I drew a scatter plot colored according to the qualitative variable. So we obtained something like this. We drew a scatter plot between two quantitative variables, invoice amount and time spent on site, and we colored each point according to the origin, which is a qualitative variable. Then there are many things we said out of this chart, out of our exploration of this chart. We said, for instance, that very globally, invoice amount decreases with time spent on site. We also said that Plutonian customers spend less time on the site compared to the others. And they spend also a bit more money on the website. So those are the gray dots. Then the blue dots and the orange dots, so those are customers from Earth and Mars. They form a homogeneous group at the bottom right. There are many, many other things we are able to say out of this chart. So this is data exploration, which we can generalize on wider data sets in terms of number of columns using the tools we'll be seeing today. So imagine the same kind of reasoning on a higher number of dimensions of variables, on a whole proteome, for instance, in biostatistics. Make way for data exploration and clustering. I will start by defining what I mean with exploring and then defining what I mean with clustering. So exploring data means simply looking for information in multiple variable data sets. Imagine you have a data set with 10 columns. I want to explore this data set without having to draw hundreds of charts. So there are some statistical techniques which allow you to do this. And among these statistical techniques, you will find methods which concentrate the information of big data sets in a few dimensions or in a few columns. So for instance, PCA and MCA and correspondence analysis do so. This is the output of a PCA I will be commenting later on. Then clustering methods allow classifying or clustering observations into sets of similar observations. So we start with a mixture of observations. These could be consumers or clients or, I don't know, patients or judges in a sensory analysis. Then clustering methods allow to sort these individuals in terms of their similarity with regards to the variables. So for instance, you can cluster individuals in terms of proteome similarity. We can segment the market according to consumption profiles. Imagine we had the consumption profile of each of these individuals. We can use classification tools or clustering methods to sort them to several groups. Here's a third example. We can classify cities in different groups based on socioeconomic criteria. Here's a small guide which allow you to choose an appropriate exploration or clustering method. According to the data type, you have different exploration tools you can use. If you want to explore a table with quantitative variables, you can use principal component analysis. This one is very, very famous. It's very commonly used. I will be illustrating it today. If you have a big crosstab or contingency table, you can explore it using correspondence analysis. Now, correspondence analysis is also quite used in marketing when you want to map the relationships between imagery statements and the relationships between products and superimpose the two maps. So map the products, the brands, for instance, brands with imagery statements. And in sensometrics, it's also used to map products with the attributes out of kata data analysis, for instance. I don't know if you're familiar with check order apply analysis, but correspondence analysis is part of the kata analysis. If you have a qualitative variables table as an input, you can explore it using multiple correspondence analysis. This one is a bit hard to implement because there's a lot of data preparation, but if it ever works well, it can have very nice results. If you have a mixture of qualitative and quantitative variables as an input, you can use PCA for mixed data. And at last, if you have several data sets and want to investigate the relationships between these data sets, you can use MFA or GPA. Now, For clustering methods, for whichever type you have as an input of data, you can use all of these methods. So technically, they all accept only quantitative data as an input, but there is a way to transform qualitative data into quantitative. But I won't be getting into these details today. Unfortunately, we don't have enough time. Something else you should know, all of these methods, except for MFA and GPA, are included in all XLSTAT solutions. So everything except those two are included in all XLSTAT solutions. Now there are a bit wider versions of these guides online. So for instance, here you have an exploration methods guide. I just click on it to show it to you. So you have a table here in which you have questions. Is your aim more exploratory or more decisional? The number of tables you have as an input, the type of data. So do you have one table of quantitative variables? Which tool should you be using for exploration? So if you have one table of quantitative variables, you can do principal component analysis or factor analysis. Of course, there are other methods. And you have remarks here telling you what is the difference between the two methods, or more general remarks. If you have a proximity matrix, you can analyze it using MDS. If you have a big contingency table, use correspondence analysis. You have methods which are adapted for more than two tables, such as MFA and GPA, which I showed you. And there are methods which are adapted just for two tables if you want to establish a correlation between two tables, or if you want to investigate causality between two tables, there are appropriate methods. So I will focus now on principal component analysis within the exploring data framework. Imagine I want to study or to explore a 4-column data set made out of height, true size, weight, and time spent on site. So I have 4 columns. I can use principal component analysis to do so. Principal component analysis summarizes a multivariate data set of quantitative variables in a few plots, and will be able to investigate the relationships among variables, proximity among individuals or observations, and how individuals or observations relate to variables. So here's a little teaser on the outcomes or outputs of PCA. This is what we call a biplot. Now there are many authors who don't really like this kind of representation. Many authors who prefer splitting the PCA outputs into observations plot and variables plot. But just for a teaser, I just wanted to show it to you. So first of all, forget about these axis titles for now, so F1 and F2. I'll tell you a bit more about them later. Just focus on these red lines, red vectors. Red vectors which are associated to different variables. So we have vector for weight, another for height, one for shoe size, and one for time spent on site. So in PCA, you'll be able to investigate the relationships between these variables in terms of angles. So two variables which are separated by a narrow angle are positively linked. So when one increases, the second one increases. So weight increases with height. If two variables are separated with a wide angle, so height versus time spent on site, for instance, the two variables are negatively linked or correlated. So when height increases, time spent on site decreases. When two variables are separated with a right angle, 90-degree angle, so shoe size versus weight, for instance, the two variables are not related. So when one increases, the second one doesn't necessarily change. Then if you focus more on the black dots, on the observations, two black dots which are close to one another and not close to the origin are similar. So to go a little bit more into the details, in order to characterize the different dots, you need to see in which direction, in which variable direction they go. So here you see that these observations go to the right, and they follow the height and the weight variables. So they have probably high scores on these variables. And on the opposite, you have time spent on site, which goes in this direction. So we can say that these observations have low scores of time spent on site. And alternatively, if we take these observations here, these customers, they have high scores of time spent on site and low score of height and weight. There's the opposite direction. So there are a lot of information that we can take out of this single chart, which is made out of 4 different columns. This is quite exciting. So you can include as many columns as you want within the same chart. So here's a very, very conceptual approach of PCA. Unfortunately, we cannot get into the details of PCA in just one single hour, so I will try to be conceptual. And for those of you who don't get this first demonstration, there will be another one which is a bit more mathematical right after. So from an initial data set in which we have some amount of information hidden everywhere. So imagine we have a data set and which hides information a little bit everywhere, but you don't really know where the information is. So you just consider that the information is homogeneously spread inside the data set. Now PCA will create an artificial data set with a number of columns similar to the number of columns from the initial data set. So we had 4 columns first, now we have 4 in PCA. The difference is that PCA will concentrate information in the first dimensions of this artificial data set. So here, the first column and the second column hold a higher amount of information as compared to F3 and F4. Don't try to interpret these numbers now. They don't really make sense for now, okay? But just know that PCA takes the information from the initial data set and tries to concentrate a maximum of information in a reduced number of columns. So from here, investigating only F1 and F2 in terms of scatter plots, for instance, allows us to have an overview from most of the information from the initial data set. So second demonstration of how PCA works. This is a toy example with 2 variables. So I'll try to run a PCA on 2 variables. Of course, don't try to do this at home because it doesn't really make sense to run a PCA on 2 variables. If you want to study the link between 2 variables, just draw a scatter plot. But this is just for explanation. I'm going to illustrate PCA with 2 variables. So first of all, what happens? Each variable is standardized with this simple operation. So we remove the mean and we divide by the standard deviation. So this helps reducing all the variables to the same scale, and it helps avoiding some variables with higher scales to contribute much more to the computation of PCA than the other variables which are measured on smaller scales. But don't worry, it's not quite dangerous, this, because you still conserve the same trend within the data. So from this, we draw a scatter plot, for instance, of invoice amount and time spent versus time spent on site. And as you can see, we still have the same trend, a decrease of invoice amount according to time spent on site, which we saw in the scatter plot with the real data before. Here, the data are just reduced to the same scale, as you can see here. Then what happens? What's the most interesting thing to capture inside the scatter plot? So the most interesting thing is this stretch in the data, this decrease, this strong link between invoice amount and time spent on site. And this is the information that PCA will seek to capture. So PCA will try to draw a line that captures the maximum of stretching in the data. And this line is located right here. So PCA looks for a dimension capturing a maximum of variability in the data. So if we project data points on the dimension, we get a maximum amplitude. And this will be the first dimension of PCA. Second step, PCA then looks for a second dimension which will capture a maximum of remaining variability under one constraint. The second dimension should be orthogonal to the first dimension. And in this case, there's only one possible direction, which is orthogonal to the first one, and it's here, dimension f2. There's no other solution. Why? Because we only had two variables at the beginning. If we had three variables, we would have had three dimensions, and if we had had four variables, we'd have 4 dimensions. But now we stop here because we only had two variables at the beginning. We only have a 2-dimension PCA. And all the dimensions of a PCA are orthogonal or perpendicular to one another. So from this, you just do a rotation of these arrows and you get your PCA chart. So this is basically what happens. And as you can see, in the horizontal axis is dimension 1 and the vertical axis is dimension 2. They are orthogonal. And in statistical software, you get the percentage of inertia or of information or of stretch, which is captured by each dimension. So dimension F1 captured 83% of the information or of the stretch in the data points from the initial data set, and dimension 2 captured 16.5. Here's some jargon, PCA. When we talk about dimension, we mean component or factor or axis. So they more or less relate to the same idea. This is an artificial column generated by PCA. The first dimension carries the biggest part of information. The second one carries a bit less information, and so on. And all dimensions are orthogonal. Inertia or variability. This is the stretch, what I call the stretch also. This is the quantity of information in the initial data set. And standard PCA, the total inertia is equal to the number of dimensions. This is not very important. An eigenvalue is a part of inertia carried by one particular dimension. So how can we run PCA in XLSTAT? PCA is part of the analyzing data menu. Here it is, principal component analysis. So here we have our data set stored in Excel, and these are the XLSTAT menus. And this is a typical XLSTAT dialog box made out of several tabs, general options, supplementary data, and so on. So the PCA dialog box is very complex. We won't be investigating all of it today. All what I will do is capture my data on which I want to build my PCA within this field here. So I can capture it either by clicking on the headers of the columns or by capturing them like this inside my Excel workbook. I want to add observation labels which correspond to my client names here, and click OK. So in the report, first thing, XLSTAT asks me which dimensions of the PCA I want to display in the charts, in the PCA charts. If I display dimensions F1 and F2, I represent 92% of the stretch of the initial data set. So 92% of the information from the initial data set, which is quite interesting. So I will just stick to these two dimensions. I click select and then I click done. So the outputs of PCA there are many of them. Unfortunately, I don't have the time to comment all of them, but I will just comment on two main charts from PCA. But you should know it's quite a complex method, so if you want to dig deeper into it, don't hesitate to do some research or to ask for a specific training. And I will comment on everything right here. So first of all, we get this output. the eigenvalues table. Here you have the eigenvalue or the information carried by each dimension. We have 4 dimensions because we had 4 variables at the beginning. So those numbers you cannot really interpret them quite directly. It's maybe easier to interpret them in terms of percentages of variability. So F1 carries 63.6% of the information from the initial data set. F2 carries 28%. And if you add up F1 and F2, you get 92%. And then you have a chart representation of this table. I will comment one of the first main charts produced by PCA. So this is the correlation circle or the variables chart, which represents F1 on the horizontal axis and F2 on the vertical axis. So these dimensions, I have selected them in the small dialog box that appeared when I clicked OK. So these are the dimensions I wanted to investigate. So this chart helps investigating relationships between variables and how to interpret these relationships in terms of angles. So as I told you, acute angle means positively linked variables such as weight versus height. Right angle means uncorrelated variables, so shoe size versus weight, for instance, and obtuse angle, so wide angles, correspond to negatively linked variables. Here there's an information which is very important also to notice in this chart. The length of the vectors. Look, there are some vectors which almost touch the circles, other vectors don't. The length of the vectors represents the quality of representation of these variables in this specific plan. So if we only have variables that almost touch the circle, which is the case here, we have the right to interpret these variables in this plan. Otherwise, imagine we had one variable which was associated to a short vector. Consequently, this variable cannot be interpreted in this plan, but could be maybe interpreted in the 3rd dimension of the PCA or 4th dimension of the PCA. But now we can stick to F1 and F2, dimensions 1 and 2, because all the variables are well represented. So how can you interpret the axes now, F1 and F2? We can say that F1 is linked to a small angle or an acute angle with weight and height. So it's positively related to weight and height. So F1 is linked to weight and height with high values on the right and low values on the left. And on the other hand, you have a wide angle separating F1 from time spent on site. So we can say that it's also related to time spent on site with high values on the left and low values on the right. So it's negatively correlated. But shoe size is almost orthogonal to F1. So F1 is not really related to shoe size. Shoe size is rather related to F2, the 2nd dimension. We have high values of shoe size at the top and low values of shoe size at the bottom. So now I'm going to add another chart, which is the observations chart. So the first representation I had shown you while I was introducing PCA is a superimposition of those 2 charts, which make what we call a biplot. But I prefer that we interpret these because on the biplots, you don't really have an idea of the length of the vectors. Okay, so it's always better to investigate those 2 charts apart. In the observations chart, we'll be able to characterize the observations. We also have F1 as a horizontal axis and F2 as a vertical axis. This is what we had chosen earlier. So if we first have a look at the first dimension, F1, and we check the coordinates of the observations on this dimension, the observations with high coordinates, so on the right, have high scores of weight and of height, and low scores of time spent on the website. On the other hand, so to the opposite, on the left, we have high scores of time spent on the website versus low scores of weight and height. And at the top here, we have one customer who is more related to access to, so it's more characterized by shoe size. So this customer has a high score of shoe size and this one a low score of shoe size. So we have characterized the relationships between variables. We have characterized the relationship between observations and variables. So in terms of interpretation, there are many things you can say out of a PCA. So total weight increases with height, time spent on site decreases with height and weight, shoe size is independent from height, weight, and time spent on site, and so on. But there's something very important I need to tell you about PCA and about exploratory data analysis tools in general. So those tools are exploratory, so you cannot really make very strong decisions out of them. You always need to use words such as tendency or trend in your speech and not having very strong assertions, because all of this is only exploratory. It allows you just to detect trends. And another thing, PCA is not always reliable. A good PCA is a PCA built on a data set which already contains at least some variables which are related to one another. And how to check if variables are related to one another, you need to draw some scatter plots between the variables and make sure that there are relationships between some of the variables. You can also, for those of you who know correlation coefficients, you can draw a correlation matrix and check whether the variables are there are at least one or two variables which are correlated to other variables. Otherwise, your PCA wouldn't be reliable. It would be built on a big noisy data set without any signal. So be very careful about this. And also know that PCA only works with quantitative data. If you want to learn about other methods, you can go to the guide by clicking on this link. So let me get back to this chart, to this PCA. So according to our PCA, customers can be split into two clusters characterized by height, weight, and time spent on site. This may help us define tailored marketing campaigns. But can we automatically assign each customer to a group? Because these circles, I have drawn them by hand. Are there any methods which will allow us to automatically assign each customer to a group? So let's see what clustering methods can do for us. So this slide, you've already seen it. Clustering methods allow classify or cluster observations into sets of similar observations. So let's see in these examples. We're going to work on this data set. This is a chocolate consumption survey. So with different respondents answering questions such as to what extent are you loyal to the brand? To what extent are you sensitive to price? Are you keen on online buying? To what extent do you prefer bitter chocolate, frozen chocolate, crunchy and chocolate? And what is your age? Question is, how can we split consumers into groups of similar profiles? The tools we can use for this purpose are clustering or segmentation tools. So we are going to run a market segmentation in a way. The clusters corresponds to a group or to a class or to a segment. So these relate to the same idea. And these tools are based on the idea of distance or similarity between observations. And there are several ways to compute distance. And the most common one is the Euclidean distance, which looks like this. So imagine we have a scatter plot of our consumers according to two variables, for instance, age and crunchy, I don't know. In order to measure the distance between this consumer and this consumer, we can use the Euclidean formula, which looks like this. So for this kind of analysis, the input data should be quantitative, such as quantitative variables. But there are solutions for qualitative variables, don't worry. So whenever variables are measured on different scales, it's very recommended to center and to reduce the data prior to the analysis. Otherwise, the variables with strong variances, or which are measured on big scales, will have a more important impact on building the segmentation. So among these tools, these clustering tools, let me cite Agglomerative Hierarchical Clustering, which is also called AHC. So it's a hierarchical clustering methods. Groups are nested in a structure called a dendrogram. It's very pretty, you'll see. Among the advantages of AHC, the dendrogram is an attractive visual, and the method can be asked to automatically detect the optimal number of groups. So in other methods, such as k-means, you are obliged to tell the software, I want to produce 3 groups or 4 groups or 5 groups out of my data. In AHC, you can force the number of groups. You have the right to do this. And you can also ask the software to define the optimal number of groups for you. Now, the following slide is an intuitive illustration of how the method works with only 2 variables and 3 clusters. So I will illustrate AHC using price sensitivity and age, for instance. I first start by drawing scatter plots as usual. So price sensitivity versus age, and each dot represents one consumer. And at the beginning of the computations, each point corresponds to one specific group. AHC will first compute all the distances, all the pairwise distances between the individuals or the groups, and it will cluster the 2 closest groups, so the 2 groups which are separated by the minimal distance, into the same group. So these 2 points, these 2 consumers, were clustered inside one single group. Then again, all the pairwise distances among the groups, so which switch from 19 groups to 18 groups, all the pairwise distances between the groups are computed again, and AHC will cluster the 2 closest groups once again. So we move on with 17 groups. And third step, all the pairwise distances are computed once again, and the closest 2 groups are clustered together. And then we continue, we carry on like this until we reach one single group. And this structure is called a dendrogram. And once we reach the complete dendrogram, can ask the software to cut it somewhere horizontally, here for instance, in order to obtain our different segments. So our segments are now defined. So this is how the method works. And this obviously can be generalized over more than 2 variables. I showed you things on 2 variables because it's easy to visualize in terms of human eyes. But of course, you can run the analysis on 10 variables, 100 variables, as many variables as you want. Now, how can I launch an AHC in XLSTAT? You have a chocolate dataset, which is here. I will go to Analyzing Data and AHC. Here it is. I will capture my data in this observations variables table. Of course, here you can select the distance you want to use. I strongly recommend staying on the Euclidean distance if you don't have a good reason to choose another one. I will add row labels here. In the Options tab, XLSTAT allows to select the center and reduce options if you ever have variables measured on different scales. Look at the age variable versus the other score variables. Age is measured on a different scale. So if I kept age like this with row values, it would play a more important role in the segmentation than as compared to the other variables. This is why I need to set all the variables at the same scale by activating these 2 options. I will ask the software to cut the dendrogram automatically with an optimal number of groups, and I would just click OK. Here again we have many outputs. Okay. Just go there. Here's the dendrogram, which has been cut here. So the optimal number of groups is 3. We have a green group, a red one, and a blue one. So the y-axis here represents the dissimilarity. And to measure to what extent 2 groups are dissimilar or different, just need to see the length of the walk you need to have from one point to another in the dendrogram. So for instance, to walk from this individual here to this one here, you need to go up the tree until here and then go down. So the dissimilarity between these 2 points is represented by this height. So the dissimilarity between this point and this point is lower than the dissimilarity between this point and this point. Because to pass from this point to this point, you need to go even further up before going down. Now, there's something important to know about dendrograms. Sometimes your data in the beginning are not really organized in clusters, so it doesn't really make sense to run a clustering on these data. And how can we more or less know this through a dendrogram? So if we have a dendrogram which starts splitting in branches at high levels of dissimilarities here, it means that it's a loose dendrogram and doesn't really, that your data is not really organized in clusters. Whereas the more the dendrogram starts being split at low levels of dissimilarity, the better your data is clustered, so the more consistent it is. So please avoid over-interpreting results you may obtain. There are many other outputs. Unfortunately, I don't have time to comment all of them, but here we have the results by object. We have the membership of each observation to a group or to a class. So we have 3 classes. Byron belongs to class number 3. What we can do now is describe or characterize these groups. So the thing that we can do is that we can copy this column here and paste it on the initial data set to be able to run descriptive statistics simply on the original variables split according to classes. So I'm going to compute the mean age for each class, the mean crunchiness for each class, and so on. I can also run what we call a parallel coordinates plot, which is a very pretty chart to represent things. Okay, so with descriptive statistics and by selecting quantitative data here and subsamples and class as subsample, I can obtain something that looks like this. So if we see brand loyalty, we have the mean for class number 1, 2, and 3 here. So we see that class number 2 has a low score of brand loyalty compared to the 2 other classes. And here we see that for age, class number 2 has a low score of age, so has a mean age of 22. Otherwise, we can also draw parallel coordinates plots. So you can follow this tutorial to see how to obtain it. And this is how it looks like. So we have on the x-axis all the variables that were used for the AHC. We can also use other variables which weren't used in the AHC, of course. And each line represents one class or one segment or one group. If I focus on cluster 3 or class 3, we have older consumers, so high scores of age, who prefer bitter chocolate and who are loyal to brands and who don't really like frozen chocolate or like less frozen chocolate and buy less online. Then the blue cluster is made out of younger consumers who prefer frozen chocolate and are sensitive to prices, and they don't like bitter chocolate. So you can draw conclusions, marketing conclusions out of this. For instance, promote branded bitter chocolate to older consumers, promote cheaper frozen chocolates to younger consumers, so on. So to sum up, we've seen exploration and exploration method, which is PCA. So the other methods more or less work a little bit in the same way. And for clustering, we've seen AHC. You need to know that k-means also and Gaussian mixture models also provide you with a membership of each individual or each observation to a group. So you can have the same analysis with a parallel coordinates plot by passing through these methods as well. So data exploration has inspired us many hypotheses, and we fished for a lot of information. Are these hypotheses valid? Make way for statistical testing, which is the topic of our next webinar next week on Tuesday. So you have a subscription link here Don't hesitate to go and to subscribe. Thank you all for attending. I will take a couple of questions before saying goodbye. We're a little bit late. How do you know that the angle right is right with either weight of or height? This is a PCA question. How do I know if the angle is right? Well, it's not necessary to measure the angle between the two variables, but if there's a tendency of a variable to go to towards a right angle, we may consider that the two variables are not related. So here, for instance, even between shoe size and time spent on site, we have a tendency to have a right angle. So it's almost right. We can say that shoe size and time spent on site are not that related to one another. What about Stanley in the PCA analysis? That's a very good question as well. So somebody pointed out this observation here, which is very close to the origin. So the closer an observation is to the origin in a PCA plan, the less you are able to characterize it using these variables. This observation, Stanley, may be more visible on other dimensions, so F3 or F4. Otherwise, you cannot really characterize Stanley with very high or low scores of all of these variables, which are strongly linked to F1 and F2. How is the interpretation if I use similarities instead of dissimilarities in the AHC dialog box? Well, the interpretation will be the same in the dendrogram. So the further the walk from one observation to the other, the more dissimilar they would be. Can we analyze ranking data? Technically, yes, if you transform them to numbers, but of course you need to have to be a bit careful in the interpretation. Thank you so much for attending. Don't hesitate to follow us on the social networks and to download the 14-day trial now if you haven't done so yet. And well, thank you very much. And I hope I talk to you once again on Tuesday.